Let's see, we've defined the Galois group of an extension, and now what we're about to do is define the Galois group of a polynomial. Remember, this class in the end is about studying the factorization of polynomials, and so there's this connection between groups and polynomials that is contained in this definition right here. So let's take some polynomial f in k bracket x. The Galois group of f is going to be the Galois group. So this is, and we'll write it like this, so is gal or gamma of f, and it's equal to the Galois group of the extension sigma over k, where sigma is the splitting field of f over k. So where sigma is the splitting field for f over k. So this is the amazing connection that Galois came up with, right? The insight of Galois is that he was able to associate a group to each polynomial, right? In this exact way. And so let's do a computation here. So, so as an example, let's let f be the polynomial x to the 4th plus 1, right, viewed in q bracket x, right? So we have this polynomial over q. And, okay, so what I want to do is I'd like to compute the Galois group of f. Now, this polynomial is irreducible over q. I believe in 482, I don't remember which homework problem it was, or homework number, but if you're in 482 last quarter, we looked at this polynomial. We're able to show that it's irreducible, even though it was reducible over every z. Is that right? It was irreducible over zp for every p, but it's still an irreducible polynomial. So let's call this omega. Omega is going to be e to the pi I over 4. We have, so this allows us to identify the roots of this polynomial, and they are, so we have the roots of f, and they are omega, omega cubed, omega the 5th, and omega the 7th. Right, and from this, now we've got all the roots, and all of them are powers of omega. So if we want to identify the splitting field, all we need to do is to join omega to q, and that will give us the other roots, right? So from this, we have that the splitting field for f over q is q adjoin omega. So a few things to note here. So let's put it here. Yeah, so let's just say note. And there's actually 3 things. So the first thing, the degree of the extension is equal to 4, and the reason is that this polynomial f is the minimal polynomial for omega over q. All right, so so that's because m sub omega is equal to x to the 4th plus 1. All right, it's a monic irreducible polynomial for which omega is a root. The second thing, oh right, characteristic of q, we know, is equal to 0, and whenever we have a field of characteristics 0, right, the extension, the degree, or not, sorry, the extension will be separable. So, the extension Q adjoint omega over Q is separable. And then the third fact, all right, since we know that Q adjoint omega is a splitting field, so the third one, Q adjoint omega is a splitting field, and so what? Oh, right. So the extension Q adjoint omega over Q is normal. So what do we have now? We have a finite, separable, normal extension. That means that we have a Galois extension. So we have, or let's see, it follows that Q adjoint omega is Galois. That's the definition of a Galois extension, right? Remember, that's one that's finite, separable, and normal. And so that's good, right? And why we like Galois extensions in the finite case, like, or in Galois extensions allow us to say exactly what the order of the group is. And so what we have is by theorem 5.5, the order of the Galois group of F is exactly equal to the degree of the extension Q adjoint omega over Q, which we know is equal to 4. Okay, so my goal in the end is to identify exactly who the Galois group of this polynomial F is equal to. And so far we know that it's a group of order 4, and so that means we have two candidates, right? It's either Z4 or Z2 plus Z2, and so let's figure out which one it is. Now, a basis for Q adjoint omega over Q is, well, it's going to be powers of omega, and it's a degree 4 extension, so we're going to have 1 omega, omega squared, and omega 3. So this is our basis here, 1 omega, omega squared, and omega cubed. And so what that tells us then, we can say, and so, let's say if sigma is in the Galois group of F, and remember the Galois group of F, let me just remind you, right, that's equal to the Galois group of Q adjoint omega over Q. Right? So that's the set of automorphisms of Q adjoint omega that fix Q. So let's see now. And so if, so this is in parentheses right here, just remembering or reminding you, and any element in here is an automorphism of Q adjoint omega. And so if we want to identify what an automorphism looks like, what we need to do is know what it does to a basis. Well, because of the form of our basis right here, all we need to do is know what it does to omega. All right? So if sigma is in the Galois group of F, then sigma is completely determined by sigma of W, or sorry, sigma of omega. If we know sigma of omega, then we know what sigma does to every single element of Q adjoint omega, right? Because they're all expressed as linear combinations of powers of omega. Okay, so there's the first thing. And so this is going to be basically sort of the format, right? The structure of a proof that, it'll be the steps that we go through when we're trying to get our hands dirty and figure out exactly what a Galois group looks like, right? The first thing is to look at a basis and recognize what outputs we need, right? Sort of a minimal collection of outputs that allows us to get a handle on how our automorphism behaves. It's not always going to be quite this simple, but in this case, right, because of the form of our basis, right, everything is determined, or every automorphism is determined by just this element right there. Okay, so also, if I look at sigma of omega to the fourth plus 1, that's equal to sigma of omega to the fourth plus sigma of 1, just using the fact, it's using two facts, right? First, using the fact that we've got a homomorphism here, right? So the power can slide inside the parentheses. Also, we know that sigma of 1 has to equal 1, so I'm just replacing 1 with sigma of 1 right there. Now, it's a homomorphism, so I can put all of this together. This is sigma of omega to the fourth plus 1. But let's see, what do we know about omega to the fourth plus 1? Well, omega is a root of our polynomial x to the fourth plus 1, so this is 0 inside the parentheses. So this is sigma of 0. Of course, that's equal to 0. So what does that tell us then? It tells us that sigma of omega is a root of the polynomial x to the fourth plus 1. In other words, sigma of omega has to be a root of the polynomial, right? Omega is a root of the polynomial, and sigma takes a root to a root. So we can say that is sigma of omega is a root of x to the fourth plus 1. So roots go to roots. And we know exactly who the roots are. Remember, those are the odd powers of omega. So it's omega, omega cubed, omega to the fifth, and omega to the seventh. In fact, let's say it like this, right? So that tells us then that our options for sigma of omega are very limited, right? It's got to be omega, omega cubed, omega to the fifth, or omega to the seventh. Okay, so now this allows us, and remember, there are exactly 4 elements in our group, right? So sigma is one of 4 possibilities. And so now I think we have enough information to write down who these are. So this allows us to identify the elements of gamma of f. Okay, so there's exactly 4 of them, and let's see how it's going to work. Well, okay, so first we could send omega, right? There's 4 possibilities, right? We can send omega to omega. We could send omega to omega cubed. We could send omega to omega to the fifth, and we could send omega to omega to the seventh. And I want to give each one of these names. So, okay, of course, this one is the identity. If it sends omega to omega, then it sends everybody to itself. Then I want to call this one sigma, right? The one that sends omega to omega cubed. This one I'll call tau, and then the last one I'll call upsilon. So we got sigma tau upsilon plus the identity. Now, remember, we've got a group of order 4, which means it's isomorphic to either Z4 or Z2 plus Z2. So to figure out exactly which group we're working with, all we need to do is figure out who the orders are, right? If we have an element of order 4, then it's cyclic. If we don't, then it's not. So since gamma of f, it's isomorphic to z4 or z2 plus z2, it suffices to compute orders. So let's just compute it here. So let's figure out, of course, the identity has order 1. And now let's look at the order of sigma. So what we do is we look at sigma. Remember, the operation is composition. So we look at sigma squared of omega, and that means sigma of omega. All right, so this is sigma of, now let's see, sigma sends omega to omega cubed, so that's sigma of omega cubed. And then, let's see, so what is sigma of omega cubed? Well, that's going to be omega to the 9th. And what I want to do is express this in terms of the basis. So let's see what we know. This is omega times omega to the 4th times omega to the 4th. That's equal to omega times -1 times -1, right? Omega to the 4th plus 1 equals 0. And so this is equal to omega. In other words, sigma of w is equal to w, so sigma squared is the identity, which means that we have order 2. Now we'll do tau. So tau squared of omega is equal to tau of omega to the 5th, which equals omega till the 25th, which equals, let's see, can I be efficient here? It equals omega to the 4th to the 6th times omega, which is equal to, so omega to the 4th is -1, raised to the 6th is 1, so it equals omega. And then if we do upsilon of omega, that's going to be upsilon squared of omega. That's equal to upsilon of omega to the 7th, which is omega to the 49, which is omega to the 4th to the 48, or to the 12th times omega. Omega to the 4th is -1, raised to the 12th is 1, and so we get omega. So what that tells us then is that the order of sigma, tau, and upsilon are all equal to 2. Okay, so we do not have an element of order 4, which means that the Galois group is isomorphic. So conclusion, Galois group of the polynomial f is isomorphic to Z2 plus Z2, the Klein 4 group. It will be useful sometimes to say more. In fact, I mean, this one was easy. There are times when you need to explore the elements a little bit further, right? Sometimes you don't get off so easy. Just say, oh, we computed the order, now we know who the group is. So it is sometimes helpful to understand exactly what how each of these elements behaves a little further. So in this sense, and we'll see why in just a second. So let me say it this way. So the action of gamma of f on the set of roots of x to the 4th, well, of f. Okay, so what happens if we apply identity? Of course, identity fixes all the roots, right? So 1 fixes the roots. Sigma, what does it do? So sigma takes omega to omega cubed and vice versa. If you compute, right, omega cubed goes to omega, while omega goes to omega cubed. So it interchanges those two, and it also interchanges omega to the 5th and omega to the 7th. Okay, so that's what tau does to the root, sigma does to the roots. Tau, it interchanges omega and omega to the 5th, and it interchanges omega cubed and omega to the 7th. And then the last one, I wish I could put it right below here in your notes. It would look a little nicer if I could. Sigma tau and then upsilon. Let's see, that one takes, that one interchanges omega and omega to the 7th, and it interchanges omega cubed and omega to the 5th. And so the point of this, I wish it was right there, but oh well. So the point, notice what is happening here. Each of the elements of the Galois group of this polynomial permutes the roots of our polynomial. In other words, each of these elements is a permutation of the set of roots. So the point, the elements of gamma of f permute the roots of f. And, you know, in some sense, that's what Galois theory is. It's the study of the symmetry. I know I've said the Galois theory is a few different things. But at least at the group level, it's sort of understanding that the Galois group permutes the roots of f in general. So this is not an isolated example, right? The next theorem we're going to show is that this is true in general. Okay, so this is theorem 5.6. So let's let f be just a polynomial. So let's let f be in k bracket x with splitting field sigma and set of roots capital R. Oh, and I want to write these out, so don't put a period here. R equal to, so this will be, what am I calling it, alpha 1? Yeah, alpha 1 through alpha n. Alpha 1 up through alpha n, so that's a collection of roots. Of course, that set is contained inside the splitting field sigma. Okay, so now the statement of this theorem then is, so we can say then, the Galois group of f is isomorphic to a subgroup of the symmetric group S sub R. Where, when I say S sub R, right, this is the group of all permutations of R, right? So, the Galois group is a permutation group, right? It's a subgroup of S sub R. Okay, so we need to prove this theorem. And so what I need to do then is I need to come up with a group monomorphism, right? A one-to-one homomorphism from gamma of F into S sub R, right? That would do it, because then it'll be isomorphic to its image. Right? So that's our goal. We would like to produce a one-to-one homomorphism from gamma of F into S sub R. So, okay, so let's pick sigma in the Galois group, and I want to write this polynomial out. So let's say, and write F equal to K0 plus K1x plus dot 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 plus K sub n x to the n. Now, so then if we look at F of sigma of alpha I, right? So I'm taking a root, plugging into sigma, right? So we look at sigma of alpha I, and then plugging the result into F, and let's see what happens. So this is going to be K0 plus K1 sigma of alpha I plus dot 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 plus K sub n sigma of alpha to the n. All right, technically, yes, all right, fine. Technically, it's sigma of alpha I raised to the n. All right, but I got a homomorphism, so I'll be able to slide that inside. Oh, and then remember, sigma, little sigma, lives in, right, so it's in, right, remember the Galois group, that's gamma of capital sigma over K, which means that sigma fixes all these K sub i's, right? So this is going to be sigma of K0 plus sigma of K1, sigma of alpha I plus dot dot dot, sigma of K sub n, sigma of alpha I raised to the n. Yeah. Which we can then combine into one thing here. So this is sigma, because sigma is a homomorphism now, I can write this as sigma of K0 plus K1 alpha I plus dot 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 plus Kn alpha sub I to the n. But alpha I is a root of our polynomial f. So inside the parentheses, that has to equal 0, which gives us 0. In other words, this sort of generalizes what we were doing in that last example. What we see is that sigma of alpha I is a root of f. We can say, so sigma of alpha I is an element of capital R. So when you apply sigma, it takes a root to a root. Okay, so now, since sigma, since sigma is 1-to-1, we know that if we look at sigma restricted just to the set of roots, this is 1-to-1. So this is 1-to-1, and right. Oh yeah. Okay. So and since R is finite, remember if you have so what we have is that sigma restricted to R is going to be mapping from R to R. If you have a 1-to-1 function, remember back to Math 248, a 1-to-1 function from a finite set to a finite set also has to be onto. So since R is finite, sigma restricted to R is onto as well. so what does that mean then? We can say thus, sigma restricted to R, well, let's see, it is a one-to-one and onto a bijection from R to R. In other words, it's a permutation of the set R. And so now we have a function that associates to each element of the Galois group an element of S sub R. So we can say, so now we have a function. I'm not even going to give it a name, right? It's a function that goes from gamma of F to S sub R. And how's it defined by? So defined by sigma just goes to sigma restricted to R. So I mean, this function right here is just the restriction function. Okay, so now if I could show that this function right here, this restriction process, is a one-to-one homomorphism, we're done. So if oh yeah, okay, so now let's take a couple of elements. So I want to show it's a homomorphism. So if sigma and tau are in gamma of F, then let's see what I need to look at. So I want to show it's a homomorphism. So we look at sigma of tau restricted to R. And then, well, okay, so how does that work? That's equal to sigma of tau restricted to R. Is that the way I want to do it? Yep. Which is equal to sigma restricted to R of tau restricted to R. There's really not any group theory going on here. This is just recognizing how restriction behaves, right? If you want to restrict this to R, well, that's going to take whatever element you plug into when you restrict it, it's going to take it into R. And so then you can just apply the restriction individually. Okay, so we can say, and thus, our function is a homomorphism. Okay, so now we just need to show it's one-to-one. So suppose that sigma restricted to R is equal to the identity function. Now, we know what sigma looks like, right? Sigma is K adjoin the set of roots, right? So it's K adjoin R. So every element is, okay, so what do the elements in sigma look like? Well, they look like linear combinations of products of alphas, right? Just think about how the proof of the Tower law, right? So every element is a K-linear combination of powers of alpha i's. Okay, so if sigma takes each of the alpha i's to, or each alpha I to itself, then it's going to take every single element of sigma to itself. Yeah, so it follows that, right? This is another example where sigma itself is determined by what it does to the, well, essentially to the basis, but really to the building blocks of the basis. So it follows that sigma of beta equals beta for every beta in capital sigma. Therefore, our function is 1 to 1, right? What did I just do? I showed that the kernel is trivial, right? If you have some element in the kernel, then that element had to be the identity in the first place, right? Sigma had to send everybody to itself in the first place. So that's it. So as a consequence, gamma of F is isomorphic to its image under the function, right? Gamma of F goes into S sub R. Right, and that's what we need. Ooh. Okay, so now what this theorem tells us is that we can think of Galois groups as permutation groups, right? They are permutations, or they behave as permutation groups, or I'm going to say this, their action on the set of roots is by permutation. Okay, so that's a good place to stop. We will see you next time, okay?